Hi friends, delighted to see you once again. Today we are discussing some 13 questions from Magnetic Effects of Electric Current, a second year chapter. And these are questions which appeared for your JEE 2025 mains exam. And this is a chapter-wise discussion, remember. We are discussing 13 questions from only one single chapter that appeared in 2025 JEE mains. Friends, here is my first question. An electron projected perpendicular to uniform magnetic field B moves in a circle. If Bohr's quantization is applicable, then the radius of electronic orbit in the first excited state is. This is electron that is projected in a perpendicular magnetic field. And we all know that when charge is projected perpendicular to any magnetic field, it is likely to revolve in a circle. Now, the circle can have actually any radius depending upon what velocity is given. That is how usually a charged particle revolves in a circle. But here, in this question, the particle is specifically an electron. Secondly, the electron is revolving in such a way that Bohr's quantization is applicable. Now, what is this Bohr's quantization? You know, this is applicable for electrons which are revolving in so-called circular orbits in atoms. When an electron is revolving inside an atom, you know, angular momentum of electron will be quantized. Angular momentum of electron will be equal to integral multiple of h by 2 pi. That is what Bohr's quantization states. So this electron, even though it is not revolving around nucleus, it is obeying Bohr's quantization. So two things must be combined here. Okay. Let us consider first of all that scenario. Here is an illustration of what is happening in the question. We have an electron that is revolving in a circle. See, this is the electron I mean. And that is given some velocity v. And these crosses are indications of magnetic field in the region. The charged particle is given some velocity v like this. Now it is taking a circle. This is the circular path in which it is revolving. Now the question is about the radius. What is the radius of this electron is a question. Radius of the path of the electron is a question. Okay, we know when magnetic field is B. Let me assume that B is a magnetic field here. And charged particle is having a charge Q. But remember, it's equal to E also because it is electron. So Q is equal to E for the particle. V is a magnetic field. Let's also assume that M is the mass of the particle. You know, when a charged particle is revolving in a magnetic field, it is likely to revolve in a circle of this radius, which is given by a certain mathematical expression. R is equal to mv by qb. This is some equation that we all know. So this is simply radius. Now, what is more important here is that this radius is in such a way that Bohr's quantization is applicable. Remember, when electron is revolving inside a nucleus, its angular momentum L is always quantized. It is an integral multiple of h by 2 pi. Or I can say L of any electron inside an atom is given by nh divided by 2 pi, where n can have any values like n can have 1, 2, 3, etc. depending upon the state of the electron. Okay, n equal to 1 stands for ground state, n equal to 2, 3, etc. stands for, you know, excited states. Okay, now let's see what is L of a particle. It is an electron, remember. It is revolving in a circle, and if R is the radius of that circle, about the center of the circle, the angular momentum classically is given to be equal to L equal to mvr because it's considered to be a point mass classically. In that way, mvr is the angular momentum. Now that mvr is equal to nh by 2 pi. So let me rewrite that Bohr's quantization here. mvr of this particular electron is equal to nh by 2 pi. This is what is mentioned in the question. Now it's only a matter of calculation. They ask you what is R here, and this R must be, of course, in terms of magnetic field B, E and all. So let's make some rearrangements here. What I suggest here is this. Okay, let's substitute for this MV. This MV is okay appearing here. I can say then MV is equal to, of course, QBR. So this MV can be written as QBR. I'm writing MV as QBR, that into R, because you see this MV is equal to this QB into R. Okay, QBR into R, which is going to be QBR squared, that is equal to NH by 2 pi. Okay, so almost over. Now, this gives you R squared as, yes, NH divided by some 2 pi into what? There is some Q into B. But remember, this Q is also equal to B. So, I am free to write this Q as E here because it is electronic charge. Okay, therefore, R is equal to, it is root of NH by 2 pi. So, it's over root of NH by 2 pi. Okay, NH divided by 2 pi into E into B. This is the general equation for the radius of the particle. radius of the path of the circular path of the particle, generally I would say. Now they ask you what is the radius corresponding to the first excited state. Remember, in the n is equal to 1, 2, 3, etc. This n equal to 1 actually stands for the ground state. So this is the ground state. Now, all the remaining numbers, 2, 3, 4, etc., they correspond to excited states. So when n equal to 2, this is considered to be the first excited state. This 3 is supposed to be the second excited state, and so on. So let's put n equal to 2 here, because they ask you what is the radius corresponding to the first excited state. So you must consider this n as equal to 2 here. So putting that value, we have it is root of 2h divided by some 2 pi into e into b, root of, that is the value for radius. So 2 and 2 cancels here. So here appears the final answer. R is equal to root of, when n is given to be 2, it reduces to h divided by what? Pi e into b, that is the radius. So this is the radius corresponding to the first excited state. Yes, that's why the option on this is 1, h by root of h by pi eb. Let me move on to the second question. A proton is moving undeflected in a region of crossed electric and magnetic fields at a constant speed of 2 into 10 to the 5 meter per second. When the electric field is switched off, the proton moves along a circular path of radius 2 centimeter. Magnitude of electric field is given to be x into 10 to the 4 Newton per Coulomb. So what is the numerical value of x is that question. Okay. It's about charged particle moving in crossed electric and magnetic fields. You know what is meant by crossed electric and magnetic field? When you have electric fields and magnetic field mutually perpendicular to each other in a region, the region is said to have a crossed electric and magnetic field. Okay, here is a scenario. I have shown a charged particle moving through a region. You can see here some arrow marks, that is some downward arrows I have shown here, which are indications of electric field in the region, and some crosses I have shown here, they are indications of magnetic field also. Now this charged particle is said to move in a straight line. They say that the particle is actually given some velocity, but the particle will move through this region without any deflection. Now why this happens, as the charged particle is passing through the magnetic field, it experiences magnetic Lorentz force. Now since there is electric field also, it experiences electric force as well. So they are likely to cancel each other. That is why the particle goes undeflected. In fact, the particle goes undeflected because the QVB acting on the particle is equal to some Q into E. The forces are balanced. That is why the particle can move in a straight line. And you also know that this happens only for a particular velocity. It happens only when V is equal to E by B. That's a condition that a particle moves in a crossed electric and magnetic field. So this equation comes from the previous one. See, when you simplify this equation, you will arrive at this result. Okay, so this is the velocity of electron. Now here the question is to determine what is the electric field in the region. If you want to find what is electric field, okay, it is here. Electric field is simply given by B into V in this experiment. Now the question is what is B? V they have given. Okay, in the question it is V is given as a data. Now B is not given. What is magnetic field in the region? That is not mentioned. In order to tell you what is magnetic field, they indirectly tell you what happens when the electric field is removed. They say that when the electric field is removed, the particle takes a circular path of radius 2 centimeter. You know that if you suddenly remove this electric field, let me try to show what happens here. Suppose this electric field is removed from this region. Okay, I'm erasing that electric field now. Then you know that the particle is likely to take a circle because of the magnetic field alone. Now that circle is having a radius. The standard equation for the radius of that circular path is R is equal to mv by qb. Now the question is what is E? So let us do one thing. In fact, the question doesn't have any indication about magnetic field. So we'll do one thing. We'll write an expression for B from this. B is given by mv divided by R. Yes, not R, it is QR. Now it's only a matter of substituting values. E is given to be B into V, so E is equal to B into V. Now B is supposed to be mv by QR. It is mv divided by QR. We found out it. Now that into we have some velocity again. Sorry. Yes, mv by QR into V. Yes, finally expression for E in this experiment appears as mv square divided by q into r. Your answer is actually in this expression. It's only a matter of putting values. In this question, it is said that the particle is a proton. Okay, particle proton means mass of proton is given here. Okay, what is the mass of proton? 1.6 into 10 raised to minus 27. So I'm putting values 1.6 10 raised to minus of 27. That is mass of proton. Velocity is given to be 2 into 10 raised to 5 meter per second. 2 into 10 raised to 5 meter per second squared becomes 4 into 10 raised to 10. Okay, I hope you're fine with that. So 4 into 10 raised to 10, that is v squared. Divided by q is proton. Proton is having a charge of 1.6 into 10 raised to minus 19 coulomb. That into radius. Now radius is said to be equal to 2 centimeter. Okay, that is 2 centimeter. In meters, it is 2 into 10 raised to minus of 2. Okay, we are simplifying this now. It is 1.6 gone. 10 raised to minus 20 is okay, 2 and 2 gone. So what remains is 2 into 10 raised to minus of, yes, how much is that? It is going to be, no, not 10 raised to minus of, it's going to be 2 into 10 raised to 4 here, I think. Yes, 2 into 10 raised to 4, that much. Newton per coulomb is the value. Simplifying this, you'll get 2 into 10 raised to 4. So the answer is 2 into 10 raised to 4. The value of x is equal to 2 here. Question was, what's the value of x? Yes, numerically the value of x is equal to 2. That was the second question, appeared from the same chapter. Okay friends, here's my third question. Yes, two long parallel wires x and y, separated by a distance of 6 centimeter. They carry currents of 5 ampere and 6 ampere respectively in opposite directions as shown in the figure. Magnitude of resultant magnetic field at a point P at a distance 4 centimeter from wire y is x into 10 raised to minus 5 Tesla. Then what is the value of x? Again, you're finding the numerical value of x. It is not a difficult question. It's almost a straight question, I must say, because ultimately it's about finding the magnetic field at a point. And we have standard equations for finding magnetic field due to straight long conductors and all. Let's see what are the magnetic fields at the given point. Here is almost a better scenario. Yes, this 4 ampere will produce a magnetic field at this point. Let me say that magnetic field is B1. Now that magnetic field B1, according to sign rule, will be outward. It will be outward to the screen according to the rules of sign. Now we have another magnetic field produced by this 5 ampere here. 5 ampere also can produce a magnetic field here. We'll be calling it B2. Now that B2, as per direction rules, it is cross also, inward also. So one field is outward, the other field is inward. B1 is outward and B2 is inward. Let me make it clear now. So this B1 here is actually a field that is outward and B2 here is going to be inward. Now the total field is going to be a vector sum of these two values. Simple as that. Okay, now let's recall that the equation for magnetic field produced by a straight conductor is given to be equal to mu0 by 4 pi, that into 2I divided by some r. And mu0 by 4 pi has a value of 10 raised to minus 7 also. Now let's find what is B1 first. Now B1 is supposed to be a magnetic field due to 4 ampere. Okay, it is 10 raised to minus of 7, which is mu0 by 4 pi, 2 into I is 4 ampere. Okay, 4 ampere divided by the distance now you see is 4 centimeter. From 4 ampere it is 4 centimeter. Now 4 is in centimeters. Don't forget to convert that into meters. So 4 into 10 raised to minus of 2. Okay, this gives you some 2 into 10 raised to minus of 5 Tesla. That's a magnetic field at the place due to 4 ampere. And remember, that's a magnetic field pointed outwards. Okay, it's outward to the screen. Now we come to B2, the magnetic field produced by the next conductor. Remember, 5 ampere produces a magnetic field B2 here. Now from 5 ampere, the distance to the point is actually 6 plus 4, which is equal to 10 centimeter. That distance is 10 cm. So the point is 10 centimeter away from 5 ampere. So while putting values, you must be extremely careful. 10 raised to minus 7 into 2I, I is okay, 5 ampere, divided by the distance r is 10 centimeters, so 10 into 10 raised to minus of 2. This is going to give you 1 into 10 raised to minus of 5 Tesla. That is the field inward at the point. Now B1 and B2 are inward and outward. Certainly the total magnetic field is going to be a vector sum of these two. So it's going to be B1 plus B2, but we know that these are vectors. The magnetic fields are inward and outward. So the vector sum will give you a magnitude of B1 minus B2 because B1 and B2 are opposite. One is inward, the other is outward. So putting values here, you have 2 into 10 raised to minus 5 minus 1 into 10 raised to minus 5. So 2 minus 1 into 10 raised to minus 5 Tesla. That's a net magnetic field. It happens to be 1 into 10 raised to minus of 5 Tesla. That's a field. Now what do they say? It's said to be x into 10 raised to minus 5 Tesla. So the answer is 1 into 10 raised to minus 5 Tesla. Actually, x is equal to 1. That is the numerical value of x in the question. Okay, let's go to the next question now. It is question 4 in my paper. Consider a moving coil galvanometer MCG. MCG is what they call moving coil galvanometer. Torsional constant in moving coil galvanometer has dimensions ml square t raised to minus of 2. So there are 5 statements given here. The first statement is about torsional constant in a galvanometer. Every spring is having a torsional constant. And you know that torsional constant for any spring is given by certain expression. Tau is equal to some c into theta, where c is known as the torsional constant, or it is also called the couple per unit twist of the spring. So here c then is equal to c by theta. This is about dimension. So I can say tau can be written better as f into r divided by theta. Now f, you know, has a dimension of ml t raised to minus of 2, and r is nothing but distance, so l, and theta is dimensionless. It happens to be some m into l square t raised to minus of 2. So ml square t raised to minus of 2 is the dimension of torsional constant is right. So what they say is that the torsional constant of C is ml square t raised to minus of 2. We are totally okay with that. So the statement A for us is a right statement. Okay. Next one. Increasing the current sensitivity of a galvanometer may not necessarily increase the voltage sensitivity. Increasing the current sensitivity will not lead to increasing voltage sensitivity. That's a fact actually, because when you think about current sensitivity of a galvanometer, you'll realize it. Okay, let me remind you of 2 expressions here. One for current sensitivity of a galvanometer. Let me call it SI, current sensitivity. It is given by BAN divided by C. That's an equation for current sensitivity. Now, voltage sensitivity is given by SV. It is equal to BAN divided by C into R. Now, here R is standing for the resistance of the galvanometer coil. N stands for the number of turns also. Yes, let us see a case where current sensitivity is increased by increasing the number of turns. Let's say N is increased here. If N is increased, certainly SI also will increase. So, SI has increased. But increasing an N may not necessarily increase voltage sensitivity, because when you increase N, you know, automatically resistance of the coil may also increase by the same corresponding value. If you increase N to some 10 times, the resistance of the coil may also increase to 10 times, cancelling the effect. So if you increase N here, R also increases without making any change in SV. So the fact is that always increasing SI will not result in an increase in voltage sensitivity. That's a correct statement. Okay. So sometimes, you know, you'll see a change in current sensitivity, but that same change is not reflected in voltage sensitivity. That's a true statement. So we are again okay with that statement. Increasing current sensitivity may not necessarily increase that. We have no objection. That is true. So B is also correct. Third one. If we increase number of turns to N times the value, then the voltage sensitivity doubles. No, not exactly, not always. At least when you increase the number of turns, you know, it will not produce any change in the voltage sensitivity. We just saw it, because when you change N, you know, R also will change in the same way without making any change in SV. So we are not okay with that. We reject that. So C is a wrong statement. Now coming to the third statement, fourth one, which is D. MCG means a moving coil galvanometer can be converted to an ammeter by introducing a shunt resistance of large value. We are against this word, because a galvanometer can be successfully converted to an ammeter by connecting shunt resistance. That is true, but the shunt resistance must be having a very small value. They say that a large value of shunt. No, usually not that. It's a small it's a shunt resistance with a very small value. So we are not okay with the large value. So the term large value is what makes that statement rejected. So I'm considering D as a wrong statement. Okay, what is E then? Yes, current sensitivity of a galvanometer depends inversely on the number of turns, of the coil, which is against our argument because SI is directly proportional to number of turns. Current sensitivity depends on the number of turns and it is directly proportional. So we can't agree with that. Okay, we'll say E is also a wrong statement. So there are only two statements which are correct. A and B are correct. A and B matramanu shari. You can go with option A. Sorry, 4. A and B are right. All right. Go to the next one. A current of 5 ampere exists in a loop, square loop of side 1 by root 2 meter. Then the magnitude of magnetic field B at the center of the square loop will be P into 10 raised to minus 6 Tesla. Then what's the value of P? Again, you have to find the numerical value of P. This is a direct question. This has to be a direct question because if a current is passed through the four sides of a square loop, certainly it produces magnetic field all around. What is a magnetic field exactly at center? I think you must remember it as an expression. In fact, you can find it by adding all the fields of four sides, but that is not what I advise. You must have certain expressions at hand. Yes, at the center of any square loop, the magnetic field is given by this expression. It is mu0 by 4 pi 8 root 2 I divided by L, where L is the length of one side. So it's a direct question in that way. So mu0 by 4 pi here is 10 raised to minus 7. 8 root 2 is okay. 8 root 2, that into what is current I here? It's said to be 5 ampere. So it is 5 ampere divided by length is given to be 1 by root 2 meter. Finished. It gives you how much? 8 into 5, 40 into 2, 80. Yes, 80 into 10 raised to minus of 7 Tesla. Or in 10 raised to minus 6, it is 8 into 10 raised to minus of 6 Tesla. That's a field produced by the loop at center. So it is 8 into 10 raised to minus 6. 8 into 10 raised to minus of 6. So your answer is 8. They ask you what's the numerical value of P. Answer is 8. Moving on to the next one. A long straight wire of circular cross-section with a radius A carries a steady current I. The current I is uniformly distributed across the cross-section. The plot of the magnitude of magnetic field with distance from the center of the wire is given by. It's a known graph to all of us, but still I'm ready to explain it. Here is a long straight conductor which is having certain radius. So it's a thick conductor. It carries a current. So let me assume that current in this cylinder is like this. Okay, I is the current. So I'm denoting the direction of current as dots on the cross section. Now the question is about finding the variation of magnetic field against distance. So when you have a straight line, for example, suppose you have a straight line drawn from the center like this, you know that the magnetic field varies along the line. At center, there is no magnetic field at all. When you go towards the edge of the conductor, the magnetic field gradually increases like this. Now, as you go away from the conductor, it decreases also. So that's a way the magnetic field can be drawn as a profile. Okay, you know, to give you more specific explanation, here is the equation for B inside. B inside any thick cylindrical conductor is given by mu0 by 4 pi some 2I into R divided by R squared, where R is a distance to the point of study. Suppose we consider a point here, then the distance is R. And capital R is the radius of the conductor also. You will notice that this B is directly proportional to R. So until we reach the edge of the conductor, B is directly proportional. Now, when you write an equation for B outside, B is equal to mu0 by 4 pi. That's given by a different expression, that into 2I divided by R. And you will see that this B is inversely proportional to R. So inside the conductor, it is directly proportional to R, and outside it is inversely proportional. So there is only one graph we can find here. Yes, of course it is 4. Yes, this one, because in option 4, you know, B is directly proportional. So that is a straight line. We know this graph. And B is inversely proportional to R, indicated by the nature of this curve. Okay, so we go with this. Option is 4. That was easy, and it doesn't require any explanation because we are familiar with that graph. Okay. N equally spaced charges, each of value q, are placed on a circle of radius r. The circle rotates about its axis with an angular velocity omega as shown in the figure. Then a bigger Amperian loop B encloses the whole circle as a smaller Amperian loop A. Here comes the next question. N equally spaced charges, each of value q, are placed on a circle of radius r. The circle rotates about its axis with an angular velocity omega as shown in the figure. A bigger Amperian loop B encloses the whole circle where a smaller Amperian loop A encloses a smaller segment also. The difference between enclosed currents IA minus IB for the given Amperian loop is. So I'm sorry that the figure is behind me, so the position of the camera I can adjust now, so I am adjusting the figure. I hope it is visible on your monitor now. This is the system of charges. They mean there are n number of charges q each arranged along the circle, equally spaced. There are n total number of charges there. Now it's a system of charges revolving in a circle. So when a system of charges are revolving in a circle, certainly that will constitute a current. Now there are two Amperian loops mentioned here. One is B and the other is A. Two Amperian loops are there. You are finding the total penetrating currents through these Amperian loops. The currents are actually called IA and IB. So that's the whole question. I hope the figure is clear for you. But don't worry, I have a better figure on the other page. Here is it. You can take a better look at the figure now. There are n number of charges. Q, they are charged particles. Q is the charge. Q is the magnitude of each charge here. And they are equally spaced on the circle also like this. Now the whole system is rotating about its central axis with an angular velocity like this. So the omega I have shown here is the angular velocity of the system. So every charged particle is revolving in circle with angular velocity omega. Totally n number of charges are there. So you can easily guess that the total charge residing on the circle is n into q, because there are n number of equal charged particles. Okay. Now, when these charged particles are revolving in circles, certainly that will constitute a current I. Let's begin with that, because when charges are revolving in circle, you know, that is equivalent to a current, an electric current. It is very similar to a current passing in a circular loop. Let us see first of all what is that equivalent current. That's simple, because when you have q charge revolving in circle with a period t, then generally the equation for current is q divided by t. Charge by time is actually current. So in that way, q divided by capital T can be considered to be the value of equivalent current. And here q is nothing but q into n, because n number of charges are there, divided by t. Now that t here, you can write t in terms of angular velocity. T is equal to 2 pi by omega. So here is it. It is qn divided by 2 pi divided by omega. So it becomes qn omega divided by 2 pi. That is the equivalent current. So let's keep that. That's a current. This revolving charges can be compared to a current carrying loop which carries a current I given by this expression. Now the question is about two Amperian loops. They are calling the Amperian loops as A and B. A, B എന്ന് പറയുന്ന രണ്ട് Amperian loops ഈ പറഞ്ഞ ഫിഗറിലുണ്ട്. അതിൽ, let me again go back to the original question. B is a larger loop. Let me show that. They say that the loop B is this. There is a bigger loop like this. Let me try to show it here. ഏതാണ്ട് ആ ഫിഗറിലെ ലൂപ്പ് ഈ കാണുന്ന പോലെയാണ്. Yes, it looks like this. It's a full loop. That's the Amperian loop. This is the loop they call B. That's B എന്നുള്ള loop. ആ B എന്ന ലൂപ്പ് ആക്ച്വലി ഈ പറഞ്ഞ സർക്കിളിനെ എൻക്ലോസ് ചെയ്യുന്നത് ഇങ്ങനെയാണ്. ഓക്കെ, ആ ലൂപ്പിലൂടെ പാസ് ചെയ്യുന്ന ടോട്ടൽ കറണ്ടിനെയാണ് IB എന്ന് പറഞ്ഞിട്ടുള്ളത്. That IB is to be determined. That is one loop, one Amperian loop. Now the second Amperian loop looks like this. It almost looks like this. ഇതുപോലെയാണ് രണ്ടാമത്തെ ലൂപ്പ്. ആ ലൂപ്പ് ഏതാണ്ട് വരച്ച് വരുമ്പോൾ ഇങ്ങനെ ഉണ്ടാവും. So that is also enclosing certain current, or certain current is penetrating to that loop also. Now the question is, what is IA minus IB? Let me begin with the first loop first of all. Let me begin with, I think, IA first of all. I'll take IA first of all. The loop is actually smaller in size. ഏതാണ്ട് ഈ ലൂപ്പാണ് ഞാൻ ഒന്നുകൂടി വരയ്ക്കുന്നത്. This is the loop I'm calling A. ആ ലൂപ്പ് ഏതാണ്ട് ഞാൻ ഇവിടെ വരയ്ക്കുകയാണ്. Okay, I'll show that that is a loop. This is the loop that mentioned as A. ഇതാണ് loop. This is A. Now, our loop will actually penetrate in the current. So it looks like this. If you are considering the revolving charges equivalent to a current, then certainly that current I, it passes through the loop like this. Now, this ambient loop will penetrate in the current IA. IA and certainly current, it is the same I that is passing through that. So IA I am writing here as an expression for IA. IA is nothing but I, which is equal to Qn omega divided by 2 pi. That is a current passing through or penetrating through the loop A. Now let's come to the loop B, reminding you once again that the loop B was this. It's a bigger loop like this. Edanda loop mottam penetrated the ingeniana. So that's the loop. Let me try to show that loop here. So let's assume that this is the second loop, that's a bigger loop. This is called B in the question. Okay. This is it. This is a second loop. That's a bigger loop. This loop is passing the current on the equator mark because it is a circle. So you can see that this is the way the current is passing through the loop. This is how it looks like. You will see that through the loop there is a current penetrating, and through the same loop the current is penetrating out also. If you are considering this current I as a current penetrating inward, certainly this current can be considered to be a current penetrating outward. The Amperian loop actually carries a net current 0 here because I current pass I pass loop. So the net current IB in this figure I can say is 0. Whatever I is penetrating in, later through some other point the same current is penetrating out also. So in that way IB is equal to 0. Now the question is, what is IA minus IB? Yes, they ask you what is IA minus IB. IA is this, IB is equal to 0. So IA minus IB is going to be just Qn omega by 2 pi. So let me come to final answer. Yes, IA minus IB, that's equal to Qn omega or Q omega n divided by 2 pi minus 0, which is equal to Q omega n by 2 pi. So the answer is Q omega n by 2 pi. You must go with option 4. Here comes the next one. Given below are two statements. One is labeled as assertion A and the other is labeled as reason B. Let's read first of all statement A. An electron in a certain region of uniform magnetic field is moving with constant velocity in a straight line path. That is statement 1. Magnetic field in the region is along the direction of velocity of the electron. That is statement number 2. So these are the two statements we have. First statement is that electron is moving in a region of uniform magnetic field without any change in direction. Can that happen? Yes, it can happen. You know that when electron is moving or any charge is moving parallel to magnetic field, this can happen. It can also happen when the charge is moving anti-parallel to magnetic field. So both cases are possible. For electron magnetic field exists in the direction move diffraction pass. That's a fact. Adevole magnetic field opposite electron charge move. So that statement looks okay because it can happen. So in that way, we are okay with statement 1 or A. Now second statement, the magnetic field in the region is along the velocity, along the direction of velocity of the electron. Magnetic field in the region is along the direction of velocity of a charged particle or electron. That's also correct. That is why the particle doesn't experience any magnetic Lorentz force here. Charged particle move actually other deflection in the direction move it is because the magnetic field is either parallel or anti-parallel. They say it is parallel to velocity. Yes, if it is parallel to velocity, it can happen. So statement number 2 is also correct. Randamata statement is correct. Onnamata statement is correct. Now, Randamata statement, first statement in the reason, I would say yes, because even exist in the magnetic field, charged particle move in the velocity parallel force adondana particle in the direction move. So statement number 2 looks like a good explanation for statement number 1. So 1 is right, statement A is correct, statement 2 is correct, and statement 2 is a good explanation for statement 1 as well. So you can go with which one? Both A and R are true, and R is a correct explanation for A also. Let's go with option. Which one is that? Yes, I think it is 3. So 3 is option. Okay, moving on to the next one. A tightly wound long solenoid carries a current of 1.5 ampere. An electron is executing uniform circular motion inside the solenoid with a time period of 75 nanoseconds. The number of turns per meter in the solenoid is. So this is a charged particle moving inside a magnetic field. The inside a magnetic field produced by a solenoid, because when you pass a current through solenoid, it will produce its own magnetic field inside, and there is an electron revolving inside it with a certain frequency or a period. Now the question is, what is the number of turns per unit length? When a charged particle revolves in a circle, it executes circular motion with a period that is given to be equal to, Q is equal to 2 pi m divided by some QB. So that's the way it was equation for a period. Okay, let me rewrite it as period T is equal to 2 pi m divided by some QB. That's the equation for period. Now B is the intensity of magnetic field there, where M is a mass, Q is the charge of the particle and all. Now what is B here? It is said that the field is produced by a solenoid which carries a current. You know that the expression for magnetic field inside a solenoid is B equal to mu 0 N into I, where N is the number of turns per unit length of the solenoid and I is the current passing through that. That's the equation for B. So let me put that equation here. T is equal to 2 pi m divided by Q into B. Now that B is equal to mu 0 Ni, because the field is produced by solenoid. Now they ask you what's the number of turns per unit length. So it's only just a matter of substituting values after rearranging. So N is equal to 2 pi m divided by Q into, yes, so what does that, T into that mu 0 also. Okay, now it's a matter of substituting values. Yes, it is 2 pi into, now m, it is electron. It is said that electron is supposed to have a mass of 9 into 10 raised to minus 31. I'll just put values. Okay, that's divided by Q. It is electrons, so 1.6 into 10 raised to minus 19 coulomb. That into period is said to be 75 nanoseconds. So 75 nanoseconds means 75 into 10 raised to minus of 9. That into mu 0. The value of mu 0 is known to us. Of course, it is given in the question also. We know that it is 4 pi into 10 raised to minus of 7. So this is the calculation. I'm saving time. Let me skip all the calculations. You will see that the total number of turns per unit length, you will get this N as 250. So 250 number of turns per meter, that's the way we get the answer. Answer will be 250, you can verify it. That was question number 9. Here comes question number 10. Consider a thin long wire carrying a current I. A particle having mass m and charge q is released at a distance a from the wire with a speed of v0 along the direction of current in the wire. The particle gets attracted to the wire due to magnetic force. The particle turns round when it's at a distance of x from the wire. Then what is the value of x? That's a question. The particle turns round, which means the particle reverses its velocity. See, in this case, a particle is projected with a certain velocity v0 in a magnetic field produced by a straight long wire. Now, initially the velocity was given in the direction of current. Now they ask you, where will be the particle later when the velocity of the particle gets reversed? So after some time, covering a certain path and all, the particle is expected to reverse its velocity, which means if the velocity is given upward in the initial moment, after some time the particle will reverse its velocity. Now, when it reverses its velocity, where will the particle be? At what distance x will be the particle? That's a question. Okay, let's try and see what's happening experimentally. There is a long wire which carries a current I, which produces a non-uniform magnetic field near it. Because the field produced by a straight current carrying wire depends on distance. It varies with distance. As you go away from the conductor, the field gets weaker. So let me show a diagram here. I think that will be best to understand what's it. Here is a diagram for you corresponding to that situation. A current carrying wire, let's say this is that wire. It's a long, straight, infinitely long wire. It carries a current I. I hope you can see some violet crosses on your screen, and these are indications of actually magnetic field. And I have tried to show that the field is a little stronger here, so the density of the cross marks are a little larger. And as you go away from this conductor, the field is getting weaker. Anyway, the direction of magnetic field is inward. According to your right hand thumb rule, when current is upward in the conductor like this, the magnetic field at the in the given region should be inward. So it is perpendicular inward to the screen. Okay. Now what is said is that there is a charged particle given some velocity in the direction of current. So possibly, I think you can see a red spot here. Let me try to highlight that this is that point. This is the charge we study. I'll assume that this is having a positive charge. Now this positive charge is given some velocity in this direction. That is what I said. Let's say it is V0. Now when that particle is projected with the velocity V0, remember the particle is moving in a magnetic field. Certainly it will experience a magnetic Lorentz force. As it is given some velocity upward, certainly it will have a force developed like this, which is nothing but magnetic Lorentz force. And this magnetic Lorentz force will be certainly perpendicular to velocity. Magnetic Lorentz force undavukkayanengil force ellappozhum velocity ku perpendicular avu. Now when such a force is continuously acting on the particle, that force will keep on deflecting the particle. If you give velocity in this way, let me just show the initial velocity given to the particle. This is the initial velocity V0 that is given. Yes, at the same instant the particle will experience a force F like this. Now this F will keep on acting on it. So as a result, the particle will start deflecting. So the particle may take a path like this. It may take a curved path. Yes, it is not necessary that it is a circle. Had the magnetic field been uniform, certainly the path would have been a perfect circle. This is uniform magnetic field. This is non-uniform magnetic field. So a curved path, closed path, closed path have a chance, and a circle have a chance. So it is likely to take a path like this. A circle. So the particle is velocity, force active, deflection particle chance. So this is the way it is likely to move. Now the question is this. Initially the velocity given was V0. That V0 may be a particle velocity chance. This may be the velocity V0 after some time. Our velocity V0, what is the distance of the particle? That is a question. It is given that initially the distance of the particle x was equal to a. Now what will be the value of x when the particle reverses its velocity? That is the question. So I only explained what the question is. I think I can give you a better figure in the next page. This is what is happening. You can see a slight blue track here. I hope it is visible on your monitor. The particle was given some velocity. Let me try to explain what this figure is. The initial velocity given to the particle was V0. At that moment, you know that there is a force acting on it. Of course, there is some F acting on the particle, which is a magnetic force. Now, that force will continuously act on the particle. And as a result, the velocity will keep on changing. Okay, at this moment, I will say the velocity has changed its direction. Yes, it is V. Now, remember, the biggest convenience in this question is that this is a magnetic field. When magnetic force is acting on a moving charge, it will only change the direction of velocity. It will not alter the speed of the particle. The velocity V0 will remain as V0 forever because magnetic field or magnetic force in general cannot do any work on a moving charge. So we can be sure that the velocity will remain as V0 at least in magnitude. Evada particle എത്തിയാലും ശരി അതിന്റെ velocity V0 എന്നതിന്റെ value മാറാൻ പോകുന്നില്ല, direction മാറി വന്നാലും ഏതാണ്ട് particle നമ്മൾ ഇവിടെ എത്തുമ്പോഴും yes, its velocity is V0. Now let's come to the question. ഓരോ സമയത്ത് പറഞ്ഞ V0 ആകുമ്പോഴൊക്കെ തീർച്ചയായിട്ടും അതിന്റെ പുറത്തുള്ള ഫോഴ്സ് ഏതാണ്ട് ഫ്ലെമിങ്സ് ലെഫ്റ്റ് ഹാൻഡ് റൂൾ അനുസരിച്ച് ഈ ഭാഗത്തേക്ക് ആവും. ബിക്കോസ് മാഗ്നറ്റിക് ഫീൽഡ് is inward. അക്രോസ് ആണ് മാഗ്നറ്റിക് ഫീൽഡ്. മുമ്പത്തെ പേജിൽ ഉണ്ടായിരുന്നു, ഞാൻ അതിൽ ഒഴിവാക്കിയതാണ്. ഓക്കെ, സോ ദിസ് ഇസ് ദ ഡയറക്ഷൻ ഓഫ് മാഗ്നറ്റിക് ഫീൽഡ്. സോ അക്കോർഡിംഗ് ടു ഫ്ലെമിങ്സ് റൂൾ ദ ഫോഴ്സ് മസ്റ്റ് ബി ഇൻ ദിസ് വേ. ഏതാണ്ട് പാർട്ടിക്കിൾ ഇവിടേക്ക് എത്തുമ്പോൾ ശരിക്കും ഫോഴ്സിന്റെ ഡയറക്ഷൻ കിട്ടേക്കാവും. ദിസ് ഇസ് ദ വേ ഫോഴ്സ് ഇസ് ആക്ച്വലി ചേഞ്ചിങ്. That is why the particle is keeping on deflecting. Let's come to the question now. They ask you, what is the position of the particle when velocity is reversed? Let us do one thing. Let's see what happens to the components of velocity here. I told you that the value of V0 will not change. Velocity V0 will keep on, will be the same throughout the motion, I can say. But as the direction of the particle is changing, the components of velocity will be changing also. So let us come to the components of velocity. Let's see what happens to components. Now forget about the force for a moment. Let us focus more on the components of velocity now. See, generally E point. Let's come to this position where the particle was having a velocity V0. If you resolve the velocity into two components, you'll see that a component is Vx along this way, and a component of Vy will be in the upward direction as well. Now these components will change certainly, because when the particle reaches here almost, when it reaches here, of course the component of Vy is downward, while Vx will be in this direction. So these components individually are changing, but the magnitude of Vx and Vy, vector sum of Vx and Vy, that continues to be V0. Vx, Vy മാറിക്കൊണ്ടിരിക്കും. Let us do one thing. But a question then എന്താണ്? Velocity V0 reverse ആകുന്നത് എപ്പോഴാണല്ലോ. അപ്പോൾ V0 എന്നത് ആണ് ഇനീഷ്യൽ വെലോസിറ്റി. അപ്പോൾ ആ സമയത്ത് പാർട്ടിക്കിളിൻ്റെ പുറത്ത് പാർട്ടിക്കിൾ സ്റ്റാർട്ട് ചെയ്യുന്ന സമയത്ത് പാർട്ടിക്കിളിൻ്റെ Vy അത് V0 ആയിരുന്നു. ആ Vyൻ്റെ വാല്യൂ പിന്നീട് റിവേഴ്സ് ആകുമെന്ന് പറഞ്ഞാൽ ഓഫ് കോഴ്സ് ഇറ്റ് ഈസ് മൈനസ് V0. അതാകുമ്പോഴേക്കും പാർട്ടിക്കിൾ എവിടെ എത്തിയിട്ടുണ്ടാവുന്നതാണ് ക്വസ്റ്റ്യൻ. So the whole question is about the vertical component of velocity. When the vertical component of velocity is reversed, what will be the position? So we conduct a study on the vertical component of velocity. Let's see what is happening to vertical component. See, initially vertical component of Vy was V0. ഏതാണ്ട് പാർട്ടിക്കിൾ ഇവിടെ എത്തുമ്പോഴേക്കും മുകളിലേക്ക് വെലോസിറ്റി ഉണ്ടാവും, പക്ഷേ ആ Vyൻ്റെ വാല്യൂ കുറച്ച് കുറഞ്ഞിട്ടുണ്ടാവും. ആ Vy ഇവിടെ എത്തുമ്പോഴേക്കും പിന്നെയും കുറയും. ദിസ് ഇസ് ദ വേ ദ Vy ഈസ് ചേഞ്ചിങ്. ഏതാണ്ട് പാർട്ടിക്കിൾ ഇവിടേക്ക് എത്തുമ്പോഴേക്കും Vyൻ്റെ വാല്യൂ 0 ഉണ്ടാവും. Now slowly when particle reaches here, slowly Vy will develop in the opposite direction. So this is the way Vy is going to change. Vyൻ്റെ വാല്യൂ എക്സാക്ട്ലി ഇനി കൂടി വന്ന് ഇവിടെ എത്തുമ്പോൾ അത് പഴയ പോലെ V0 ആവും. So let us study what is happening to Vy. You will notice one thing, that Vy is changing. If Vy is changing, certainly there is an acceleration along the y direction. So since Vy is changing, we must expect actually an Ay here. In the y direction, there is an Ay. ഈ y directional Ay ഉണ്ടാവാനുള്ള കാരണം ശരിക്കും y directional force ഉള്ളതാണ്. ഏതാണ് ഈ y directional force? I'll explain. Let us come to the force once again. See, I'll come to the force acting on the particle at some arbitrary position. ഈ സമയത്ത്, look at this position. ആ സമയത്ത് ആക്ച്വലി പാർട്ടിക്കിളിൽ ഈ ഡയറക്ഷനിൽ, അക്കോർഡിംഗ് ടു ഫ്ലെമിങ്സ് റൂൾ, ദ ഫോഴ്സ് ആക്ടിംഗ് ഓൺ ദ പാർട്ടിക്കിൾ ഇസ് ദിസ്. ആ ഫോഴ്സിന് ഓഫ് കോഴ്സ് ഇറ്റ് ഹാസ് എ കോമ്പണന്റ് ഇൻ ദിസ് ഡിറക്ഷൻ, ദാറ്റ് ഈസ് ഗോയിങ് ടു ബി സം Fy. അതിന് എക്സ് ഡയറക്ഷനിലും കോമ്പണന്റ് ഉണ്ട്. ലെറ്റ് us study y direction only. Forget about x direction of force now, x component of force now. F is having some y component. എങ്കിൽ ആ Fy is downward ആണ്. And remember, the particle was having some Vy in the upward direction also. So when you look at this part, just look at this part, you will see that the Vy is being affected by the component Fy. That is why Vy is keeping on changing. So if there is any acceleration in the y direction, it is because of the Fy. So Fy produces actually the acceleration. So I can say that the Ay is because of Fy, and force by mass is acceleration. This is our first step. Acceleration in the y direction is Fy divided by m. Now let us see what is this Fy. What is Fy? Fy is actually the component of magnetic Lorentz force in the y direction. There are many ways to find it. You can of course find the full value of F first. ഈ ആംഗിൾ തീറ്റ ആണെങ്കിൽ Fy നിങ്ങൾക്ക് Fy equal to F cos theta എന്ന് പറഞ്ഞെഴുതാം. But I don't advise that. അതിനേക്കാൾ നല്ല ഇവിടേക്ക് ആംഗിളൊക്കെ കൊണ്ടുവരുന്ന പറഞ്ഞാൽ ഇറ്റ്സ് അഗെയിൻ ഗോയിങ് ടു കോംപ്ലിക്കേറ്റ് തിങ്സ്. പകരം ഈ Fy ഉണ്ടാവാനുള്ള റീസൺ, F ഉണ്ടാവാനുള്ള റീസൺ V0 ആണ്. Why Fy? I can say that it is because of the component Vx of the particle. പാർട്ടിക്കിളിൻ്റെ വെലോസിറ്റി V0 ആണ്. ആ പറഞ്ഞ പാർട്ടിക്കിളിന് Vx എന്ന് പറഞ്ഞൊരു കോമ്പണന്റ് ഉണ്ട്. ആ Vx കാരണമാണ് ശരിക്കും Vy ഉണ്ടായിട്ടുള്ളത്. So the Fy is actually because of the component Vx for the particle. And the Vx I can show in this figure like this. This is actually the Vx. Now I am saying you can conveniently forget about the actual force. Forget about it. We'll only take the component. Now this Fy is caused by this Fx. That's the reason for Fy. To find what is Fy, we can use equation QVB. Now this is going to be QV into B, that is Fy divided by M. Now what V? Of course I told you that it is this V. The V that I meant is here Vx. Vx produces actually this Fy. A component of Vx is responsible for the component of F in the y direction. So this Fy can be written as Q into Vx into B. Let me rewrite this as Vx. So Q Vxb divided by M is Ay. Acceleration in the y direction is Q Vxb by M. Okay, that's our first step. Let me write that step in detail here. The acceleration in the y direction is equal to Q into Vy, sorry, not Vy, it is Vx, that into B divided by M. This is how we begin. Now it's a matter of calculus, because the question is what will be the position of the particle when Vy becomes negative V. So we need some integration here. Okay, first of all, Ay, acceleration is dV by dt. But if it is Ay, we must say it is equal to dVy divided by some dt. That's the way I can write acceleration in differential form. But here you see acceleration is caused because of an opposite force. I told you that Vy is upward while Fy is downward. Certainly that will produce a retardation only, at least in the beginning. Okay, when compared to the initial velocity, taking the initial velocity as positive, you will see that the acceleration is negative. So in that way, this Ay must be written as minus of dy by dt. See, because it is retardation, at least in the when you come to the initial velocity, the force was opposite. Okay, so in that way, it was a retardation, at least in the beginning. So Ay is minus of dy by dt. Now, this Ay can be rewritten as minus of dy by dt. Okay, it is minus dv by dt in the y direction. That is equal to qvxb. Okay, q into b divided by m. Now, what is this vx? Velocity in the x direction can be written as, of course, dx by dt, where x is the x coordinate of the particle. Vx is generally dx by dt, but here also you will see that x is decreasing, because when the particle is here, I'll just show the initial position of particle, it was here, later it comes to this point, see, the x is decreasing, this was the x, later this is the x, pin name x gorenu. So x is keeping on decreasing. As x is decreasing, of course, vx must be given minus dx by dt, because x is decreasing here. So in order to compensate for that, I have put a negative sign also. So let me put that Vx as minus of dx divided by dt. So this is the way I have rewritten Vx. Okay, now double negative cancels. Let me write it once again. dv by dt is equal to, no, not only negative, of course, that dt is also cancelled. I'm going to cancel two things here. Minus dt is okay, cancel, minus is gone. So it's going to be much more convenient now. It is dvy is equal to some qb divided by m, that into dx. This is the equation we are going to integrate. Now let's see what is this B. What is this B actually? B is a magnetic field in the region. Now since we are studying the charged particle at least here, it's an arbitrary position, then B means B, the magnetic field there. Now what is a magnetic field there? Of course it is given to be, it is given in the terms of x. It depends on the x anyway. And we know that magnetic field at any point, this B is given by mu 0 by 2 pi into some I divided by x, because it's a straight long wire. If the distance to this point is x, certainly that is the equation for B. So I'm using that B here. The equation for B I'm substituting now. So I'm just substituting for this B. Okay, this into, all right, I'll write in the next step. It is equal to dv by divided by dt, that is equal to q divided by m, that into B is mu 0 divided by 2 pi, that into dx. Now it is I by x into dx. This is it. Now we integrate both sides in order to get a velocity position relationship. This is the way I advise. We take the integrals on both sides. Now let's use the limits very carefully. It is x the variable on the right direction and vy the variable on the left side. Okay, on the right side it is x. Let us see where is x beginning and where does x end. This is the initial position of the particle. At initial position, you know, this x was given to be equal to a in the question. So x equal to a is the initial position. So I'll say this is x is equal to a. Now the question is, where will be the particle when it reverses its direction? So this is what they're asking. This is, let's say, x equal to b. Okay, now b is to be determined. At what distance will the particle reverse its velocity? Okay, so x is equal to a to x is equal to b. That's the limit of integration. Okay, this is x is equal to b. All right, Sherry. Now let's come to the velocity, the left side. Left side velocity dv by dt, dvy by dt. What are the corresponding limits? Let's see. Okay, this one, x is equal to a. When x is equal to a means this was the position where x is equal to a. x is equal to a, the Vy was equal to V0. And when x is equal to b, you know, the Vy has become negative of V0. So one limit is V0, the other limit is minus of V0. So the signs are very important here. When x is equal to a, I can say Vy is equal to plus V0. And when x is equal to b, Vy is equal to minus of V0. That's the way I can give limits. Now it's only a matter of integrating. I think I unnecessarily took that dt was cancelled earlier. Okay, sorry for that. Now let's integrate both sides. Integral of dvy is Vy. So Vy between plus V0 and minus of V0, that's the limit on the left side, equal to, it is q by m into mu 0 divided by 2 pi, that into I is also there. Now 1 by x dx, we know that it is log. So it is log x between x equal to a and x is equal to b. It's almost over, I think. Integral of Vy between two limits minus V0 plus V0 is going to be minus of V0 minus plus V0, which is going to be 2V0. Okay, so minus of 2V0 is equal to, that's equal to what? Q by m times mu 0 I divided by 2 pi. That into log. When you put limits here, log x, log b minus log a will become log of b divided by a. Okay, that's it. Let me rewrite the equation here. Let's say what is the value of a. Okay, I'm writing equation for log b by a now. Okay, log b by a, that is equal to, let me make carefully the rearrangements. It is 2 pi m into minus of 2v is going to be minus of 4 pi m into v0. Anything missing? Yes, divided by q mu 0 I, divided by q mu 0 times I. That is the equation we got. Anything missing? Let me confirm. Yes, nothing missing. Now we come to the final step. It is log. If log b by a can be written in this way, then you know that b divided by a will be written as e raised to minus of 4 pi m v0 divided by q mu 0 into I. You know the rules of that. Now they ask you what is b. Okay, so finally here comes the answer. Okay, it is a, e raised to minus of 4 pi m v0 divided by q mu 0 into I. That is the expression. That is the value for b when the particle reverses the direction of velocity. So initially the particle was having some v0, finally it becomes again v0, but it is in the opposite direction. So if you consider one as plus v0, remember it becomes minus v0 later. Now remember, it continues to be v0 no matter where the particle reaches, because the particle is moving in a magnetic field. As long as magnetic force is acting on a particle, it can only change the direction. It will not change the magnitude of V0. So that's the biggest convenience of this question. But the difficulty is that you'll have to deal with components and all. Which component is responsible for which component of force, you must be aware. Okay. So let's come to the final answer. What was it? It is A E raised to minus of 4 pi m V0 by q mu 0 I. That's why the option is 1. Here is the next one. An infinite wire has circular bend of radius A and carrying a current of I as shown in the figure. The magnitude of magnetic field at point O at the center of the arc is. You can see a circuit here which is a combination of a 3/4 circle and 2 long wires. You are required to find what is the total field at the center of the circle. So let's first of all analyze the magnetic field produced by the whole system. You will see that there is first of all a 3/4 circle like this. Okay, that circle will produce a magnetic field of its own at center. That is expected. So there is a magnetic field of B1 produced by 3/4 circle. Now this part, I am highlighting this part. There is a semi-infinitely long part here. That will produce a magnetic field of B2. Okay, so we have a B2 also expected later. Now finally, this part, I am highlighting this part. Look at that. This is the part carrying a current of I. Now that current will not produce any magnetic field here, because when you have a straight wire carrying a current I here, it will not produce any magnetic field at points like this. You'll see that at these points you'll see B is equal to 0. All these points will have actually magnetic field B as 0. So you don't have to worry about this section at all. at least that will not produce any magnetic field here, or the B produced by that part is going to be 0 at center. So the field at center is only contribution of two parts here. One is the 3/4 circle and the other is this part. These are the two fields we consider here. Okay. Now they are independently given by expressions, you know. I'll give you the expression for, first of all, magnetic field due to a circular arc. If you have an arc which subtends an angle theta, then the magnetic field at the center of the circle is given by mu0 by 4 pi, that into I by r, where r is the radius, that into theta. That is a general equation for field produced by any circular arc. Now here, what is that theta? It is said that it is a 3/4 circle. So a 3/4 circle will subtend an angle of 2 pi divided by 3, sorry, 3 pi by 2, 3 pi divided by 2, 270 degree at the center. So the theta for this particular 3/4 circle is actually 3 pi by 2. So we have to use that. Let me put the value of B1. B1 is equal to mu0 divided by 4 pi into I by r. Here r is a, the radius of the loop. That into theta is going to be 3 pi divided by some 2. Okay, that is B1. Now in the sight, you know, the magnetic field is inward, because when you apply the right hand thumb rule, you know, you'll see that the field is inward. So here the field is going to be inward. So I will just show the direction of field in the term here. It is just inward. Okay, that is B1. That's a field due to the circular part. Now we have the straight part, which has a which is going to be semi-infinitely long. Look at this. This is the conductor, which has its end here, and it's semi-infinitely long conductor also. Semi-infinitely long conductor will produce magnetic field if this is the conductor, and if you choose a point here which is at a distance of A, then there is an equation for that. Remember, the magnetic field was given to be equal to mu0 divided by 4 pi into just I divided by A. That's a field produced by infinitely long, semi-infinitely long wire at the edge level. So this is the second field here. Let me use that as B2. Okay, so B2, the field produced by the semi-infinitely long part is mu0 by 4 pi, that into I divided by A. So these are equations you must get by heart, you know. Now that field also is inward here. Sorry, in this case, yes, that field is also inward here. When you apply your right hand thumb rule, you'll see that that field is inward. So that is shown to be again inward. Both the fields are reinforcing each other. So the total field is going to be B1 plus B2. I'll finally come to the net field at the place. It is vector B1 plus vector B2. But since they are in the same direction, it's just a sum of B1 and B2. Okay, let's add them carefully. I'll take the common factor mu0 by 4 pi as common. I by A is also common for both. I think in B1 it is 3 pi by 2 and B2 it is 1. Okay, this is the total field at the center for the given situation. So it is option 4. Okay, moving on to the next one. Consider a long straight wire of a circular cross-section carrying steady current I. Current is uniformly distributed across this cross-section. The distances from the center of the wire's cross-section at which the magnetic field inside the wire and outside the wire is exactly equal to half the maximum possible magnetic field. You know, for a cylindrical wire, the magnetic field varies with distance. I'll just try to show some figure. Okay, this is supposed to be that cross-section of that conductor. Believe that it's a long straight conductor. Okay, I'm only showing the cross-section here. Now remember, this is the center of that circle. It carries a current I. Current is supposed to be uniformly distributed inside. Okay, let's say I is a current. Now you know that magnetic field at various points are given by various expressions. If you want to find the field at any point inside at a distance r, then you know the magnetic field inside is given to be B is equal to mu0 divided by 2 pi. Okay, I'll write in 2 pi. That into I into it is going to be r divided by some r squared when it is a point inside it. Now for a point outside, you know, when you take a point here, certainly the magnetic field is given by a different expression. In that case, it is mu0 divided by 2 pi, that into just I divided by r. That's a field at any point outside. Now, you know the magnetic field at the surface is maximum. When you take r is equal to capital R, the field is supposed to be maximum. So let me say B maximum here is going to be mu 0 divided by 2 pi that into I divided by capital R. That's a field, that's a maximum field you can expect due to any cylindrical conductor. Now the question is, where exactly can you expect field to be equal to half the maximum? B maximum by 2. The field B dash must be equal to B maximum by 2. Which are the points at which this can be expected? That is it. So B maximum by 2 means mu 0 by 4 pi. So let me put first of all the value of B maximum by 2 in this expression. You need to find what is the distance R to that. Okay, I'll put it. B is given to be B maximum by 2. So B maximum by 2 means it is mu 0 divided by 2 pi that into I by R, that is B maximum. Now by 2 means, okay, half. This is equal to, yes, mu 0 divided by 2 pi that into IR divided by R squared. Solving this, you'll get some value for R here. Okay, simplify this, you will see that this R is equal to R by 2. When capital R is the radius of this conductor, at a distance R equal to R by 2, you will find field to be equal to half the maximum. So that is one answer, half the radius. Now the next answer is for a point outside. You will find B maximum to be, B to be also equal to B maximum by 2 at a point outside also. So this is the equation corresponding to field outside. When you give a B as B maximum by 2 there, let me see what happens. It is mu 0 divided by 2 pi that into I by R, that is B maximum, that into 1 by 2 is equal to mu 0 divided by 2 pi that into I divided by small r. Now when you simplify this, you will see that mu 0 by 4 pi is going to get cancelled. Okay, I by R is gone, I is gone. At least you will see that in that case R will be equal to 2R also. So these are the 2 points where we can expect field to be equal to half the field on the surface or half the maximum field. So R equal to R by 2 and R equal to 2R. These are our answers. Okay, let's go back to the option. Now see, here it said that the radius is A. So my answers would be these. Okay, yes, R equal to one point is A by 2 and the next point is 2A. So half the radius and twice the radius. At these 2 points you can expect field to be B maximum by 2. So which could be that? You must go with option A. Sorry, option 3, I'm sorry. Yes. Here comes the last question from moving charges and magnetic effects. The magnetic field inside a 200 turn solenoid of radius 10 centimeters, 2.9 into 10 raised to minus 4 Tesla. If the solenoid carries a current of 0.29 ampere, then the length of the solenoid is how much? In terms of pi, you have to express it. It's a direct question. You are finding the field length of the solenoid which can give a certain magnetic field. So it's only about expressions. Magnetic field inside any solenoid is most simply given as mu 0 Ni, where N is supposed to be the number of turns per unit length. Now if you want to write the number of turns per unit length in terms of length of the solenoid, that's also possible, because if capital N is the total number of turns in the solenoid and L is the length, then N is equal to N by L. Let me use that to redefine the equation. It is mu 0 into N by L that into I. The equation is rewritten. They ask you what is L, the length. So I'll rearrange the equation to get L. Okay, L is equal to mu 0 into capital N that into I divided by, what is that? It is B. Mu 0 Ni by B. Did I miss anything? No. They ask you what is L. Now let me start putting values. L is equal to mu 0 is 4 pi into 10 raised to minus 7. That into number of turns in this solenoid is said to be 200 turns. That's the total number of turns in this case. So that is 200. Let me write it as 2 into 10 raised to 2. 200 I mean. Okay. That into I is 0.29. So that is 0.29 in amperes divided by magnetic field is supposed to be 2.9, that into 10 raised to minus of 4. Okay, this is it. 2.9 10 raised to minus 4. Simplify this, let's see. Okay, 2.9.29 cuts, okay, 10 times. So this becomes 10 raised to minus 3. Okay, you have a 10 raised to minus 7 here. Altogether, it's going to be 8 pi, isn't it? Into 10 raised to minus of 2 meter. 8 pi 10 raised to minus 2 meter, which means 8 pi centimeter. So the answer is 8 pi centimeter. But already there is a pi in your answer. Remember, they ask you how many pi's. So the answer is 8 pi. Answer is 8 pi centimeter. So the numerical value of this answer is 8. 8 is a numerical value. So thank you very much for watching. We'll meet again with another video. Bye.